So yeah, hello and welcome guys. Today we are going to talk about the CodeChef long challenge problem called random walk. So I'm gonna explain how you could have approached this problem, and then also I will talk about a little bit details about the implementation of this problem. So this is the agenda. But before we actually start discussing the problem, let's wait for a few moments, and we'll start soon. And for those of you who do not know me, I am Triveni Mahatha, and I am currently residing in my hometown in Bokaro. But my competitive programming journey it starts from 2013, early 2013, when I started doing programming contest and started from CodeChef. Then I also used to practice from Spoj, and the long challenges has been like very fascinating and very interesting for me. I always used to learn new things in all the long challenges that I used to take part, and still I think like that must be true, because long challenge provides you a lot of good problems where you need to put some effort and research to solve some of the hard problems, so, which is very fun, and like you have sufficient time, so you do not have any rush, right? So that's why like I like long challenges very much. About me, I also took part in many other contests like ICPC. I qualified for ICPC World Finals in 2016, and also I have qualified in many other programming contests like Snackdown. I have qualified for 4 times Snackdown finals under the India quota, and I have also been problem presenter in ICPC regionals. Then I have also trained ICPC teams in Amrita, and trained, of course, like I trained students, juniors in my college when I was in college as a coordinator of the programming club. I but these were like some of the things that I really enjoyed doing this. And yeah, from the very beginning, I like to discuss like anything related to competitive programming, and that's why I'm here today. We are going to talk about the random queries problem. If you have any questions, please post a comment so that I can like see the comment here and I can answer that. Okay guys, so let's start now. I am going to share my screen. So Vinita, can you share my screen? Yeah. So I hope you are able to see my screen. The problem is random walk from this March CodeChef long challenge. So this is from March 21 CodeChef long challenge. What is this problem is about? So you are given a tree. You are given a tree, something like this, and in this tree you are allowed to do some random walks. So you will be given some updates, or like some random walks, let's call them some random walks. So you do some walks. Okay, you are some walks, and then you will have also some queries. What are these random walks? So you will be given a node. For example, let's say like you are given this node, so you start a random walk from here. So whenever you are at some node, and if you have like some choices to take, you take them with equal probability. So that means from when you are here, you have like 4 options to choose from, right? So with 1/4 probability, you can take any of these 4 paths. Okay. So with 1/4 probability. So let's say like you took this path. You took this path and you are now here at this node. So from here you have only 2 possibilities left, this possibility and this possibility. You cannot take the path which you have already taken. So you cannot visit a node which you have already visited, sort of, right? Like, so it's not a fully random walk, but like you are doing a random walk with a exception that like you cannot take the same path which you have already taken, right? So here you have only 2 possible paths, and both of them are equally likely, right? Both of them are equally likely. So you can take any of these two paths with 1 by 2 probability. So let's say like you took this path, and here from here you do not have any more choices, so you stop. So you stop here. Okay. So what the query is going to look like? So the queries are going to look like one, indicating that this is a random walk, indicating that this is a random walk, and then the node u. So this is from where you start the random walk. Start from here, and the other parameter will be given d. This is the maximum length of the walk, max length of the walk. This is what you are given. That means, so you stop when either you do not have any other choices to move from, then you stop, or if you have already walked a d length, then also you stop, right? So while making this kind of random walk, you are visiting some of the nodes, right? Like, so you are visiting some of these nodes. So for example, if you took this path, then like you visited these nodes. Similarly, you could have taken like another path, like you could have taken this and you could have taken this path. And if the tree were even longer, something like this, maybe this, and let's say like d is equal to, in this example, let's say like d is equal to 3. Okay. So, and you were taking like from here, like you took this with 1 by 4 probability. Now you have two more choices. Each of them have 1 by 2 probability, right? Equal probability. And with 1 by 2 probability, you took this path. And then you have again 1 by 2 probability. So with 1 by 2 probability, you took this path. Here also you stop. You stop here. Why? Because d was given to be 3. So that means like you cannot take a random walk which is longer than d. Okay. So this is 1, 2, and 3. So this path is already length 3. So we stop here. So clearly one can see that whenever you start a random walk from some node u, then you have like a lot of possibilities. And whenever you are at some node, and if you have like some outgoing edges which have not been visited yet, then you have to take all of them with equal probability. Okay. So this is the problem. This is how you do random walks. Now the question is, then there will be like some queries, like, so the query can be of this form. So in the query you will be given 2 and u. So 2 indicating that this is a query, this is a query, and u indicating, tell me the expected number of visits to this node, right? So let's say like you are given a u, for example, let's say like you are given u equal to this as a query to this node. This is the query. So you have to tell me on an on an average how many times you will visit this node if you do all these walks, um, random walks, right? So clearly you can see this is a random experiment, and in a random experiment, there is like certain probability of happening of something. So when you did the first random walk, for example, for like this first random walk, just a second. In fact, like we have only done one random walk here. So in this random walk, what is the probability that you will visit this node? So the probability is only 1 by 4, right? So when you are here, so you have 1 by 4 probability of taking each of them, and if you take with 1 by 4 probability here, then you are going to visit this. So uh, the answer for this case will be 1 by 4, right? Answer for this case will be 1 by 4. So clearly you can see this is a random experiment going on here, and you are asked to find the expected numbers of any node. So yeah, so before we go on and like actually solve this problem, let me ask you a question. So the question is, if from node u there are total p paths of length less than equal to d, then will all the paths be traveled with equal probability? All the paths of same length, let's say. So what I'm asking is, if you are doing a random walk, for example, in this example, so if you are doing a random walk from here, so this is one possible path, and like another possible path is this of same length, of length equal to 2, for example. So is it equally likely that like this path will be traveled versus this path will be traveled? So is it like uniform? Because in the problem you are given like some information about the probability distribution. So I'm asking, is it correct to say that all the paths of same length are equally likely to be traveled of same length if you do a random walk from node number u? What do you think? So clearly you need to notice here that answer is no. They are not equally likely. So answer is not equally likely because clearly you can see the probability in the problem. First of all, like in the problem it is not given, and whenever you have a choice, then like each of the choices are equally likely that you pick. And if there is a more branching on one side and if there are less branching on the other side, then they are not equally likely. For example, you can quickly construct a counter example, right? So for example, if you do a random walk from here, a random walk of length 2, length 2, so this is one possible walk. So what is the probability of happening of this? This is true with probability 1 by 2. What is the possibility of tracking this? This is possibility 1 by 4, and this path is possibility 1 by 4 if you do a random walk from here, right? So clearly you can see like these two paths. So this path uh, and let's say like this path are of same length from some node u, but they are not equally likely, right? So one quick thing I wanted to know so that you have a complete understanding. Now let me see if you have any question. Mayank Nigam is saying that the screen is not visible. Can someone else confirm that the screen is actually visible? Can someone tell me that the screen is visible? Just a second. Okay. Okay. Cool. So this was just like one a small question. Now, how do you solve this original problem, right? So how do you find this original problem? Two quick things to note here. One quick thing. Note one. So if you are given a tree like this, and if you are trying to find what is the expected number of visits for this node, right? So if let's call this node I, and if xi denotes that um, number of visits of node I, right? So clearly, and let's say let's denote this xi comma j be a random variable, that this is equal to true if node I was visited because of a random walk from some node j. So this is, for example, a node j, and a random walk was started of some particular length. So it can like possibly visit this, or it can also possibly not visit this. So like it's a random walk, the possibilities are there. So xij denotes that if you did a random walk from j, then xij is true if node I was visited in this random walk. So like if you followed this path, then xi is true, otherwise xi is not true. Okay, so clearly, if you have a list of all the updates, all the walks, then xi is nothing but summation of xij for all j, such that there was a walk from j, right? So this is like very clear, and you must have like noticed by now that this is nothing but what I'm trying to do is a indicator random variable, indicator random variable, right? So therefore the from the linearity of expectation, it is very obvious that the just a second, the expected value of xi is nothing but summation of expected value of xij. And because like this guy is a random variable, indicator random variable, you know that e of x of ij is equal to the probability with which xij is equal to true. And this is nothing but, like in English you can read that probability that ith node was visited because of a walk from j, some particular walk, that, and of course like there is a summation here, so like you need to this. Okay, so clearly like you can see that the only thing that we need to really solve now is this, that what is the probability that if some random walk happened from node number j, then what is the probability that the ith node was visited, right? So what is the probability for that? Like once you do that, then like you just need to sum that all up and you have the answer because of the linearity of expectation. This is very fundamental if you know linearity of expectation. So, like this is whenever you deal with expectation, most likely you will have this. So now let's draw a graph or tree like this. Let's draw some more nodes. So tell me, if there was a random walk from, for example, this node, okay. So if a random walk was from here of length d, okay, and you are at like some particular node, maybe let's pick this node, okay. So you are at some particular node j, and then what is the probability that this guy will be visited, right? So what is the probability that this guy will be visited, and let's call this node I. So what is the probability that xij is equal to 2? What is this probability? Okay. So clearly like you can calculate that, like to visit j you need to take a route like this, you need to take a route like this. Of course, if d is less than 3, if d is less than 3, then this answer is 0, that like you cannot ever like reach here. Otherwise, if d is greater than equal to 3, if d is greater than equal to 3, then what is the probability? So what is the probability that you take this path? What is the probability for that? Probability of taking this path is, so you have like four paths, four possible choices here, and all of them are equally likely. So possibility that you take this is 1 by 4. From here you have two equally likely chances, right? Like here 1 by 2 and 1 by 2. So you take this with probability 1 by 2. And here again, like you have two choices, and if you take this with 1 by 2 probability, then like you reach here. So what is the overall probability that you reach here? That is nothing but 1 by 4 into 1 by 2 into 1 by 2, which is equal to 1 by 16, right? So clearly like one can see this is the expected value of xij, and basically what we need to do is we need to do this thing for all the updates because of the linearity of expectation. This is the all This is what like is remaining. So if you formally write this thing, then the probability of like visiting v from u is how much? It is nothing but 1 by degree of u into, because like when you are at node number u, then like you have degree of u choices, right? So you take the one uh, that is in the path from u to v, right? Like, so you take this guy with probability 1 by degree, and then you take degree of some like intermediate nodes, like some xi, let's call them xi, degree of xi minus 1, right? And you take a product of this, right? Why you take degree of x minus 1? Clearly here you can see that like when you are at any intermediary node, then you must have taken like one of the edge to reach here in the first place, right? So when you have taken that edge, then like that option is not there with you. So if it has a degree equal to 3, for example, in this case, but you have only two choices. So we have degree equal to 3, but you have only two choices, right? Because you have already taken this path. So in general, this is true for all the nodes, right? So you, this is like obvious from here, right? So if you have this p, the probability to visit v from u, if there is a random walk at u, then what you need to do? You basically need to do this 1 by degree of u into 1 by degree of xi minus 1 product for all the intermediate nodes xi. This is all the intermediary nodes xi in the path u to v. So if you use this formula in this particular example, to just for like clarity, so 1 by degree of u, what is the degree here? Degree is 4, so 1 by 4, and this is the intermediary node and this is the intermediary node. Like you do not have to take this, like this is not intermediary nodes, right? So what is the degree of this? Degree of this is 3, right? Degree of this 3, so 1 by 3 minus 1 into what is the degree of this guy? So 1 by 3 minus 1. So basically this is nothing but 1 by 16, which we have like calculated otherwise also. Clear? The probability that you visit node v if you start from node number u. Okay. So this basically sort of like solves our complete problem. Now the only, like conceptually this solves our problem, but the only thing that remains to solve right now is like how do you basically do this thing efficiently, in the sense that how, what kind of data structure do you use, and like how you can solve this problem using that data structure. So that is the only thing remaining. Conceptually you have solved this problem, right? So you basically keep track of all the updates, and whenever you have a query at some point, then like you iterate through all the updates and you calculate the probability using this formula, and you take the summation, right? You take the summation because of this linearity of expectation, and that's how you are done. Now how do you like solve this problem efficiently? What kind of data structure you can use, right? Like this is the only portion remaining today. So if you have any questions, please ask, otherwise let me go ahead. And so before we use any data structure, let's try to solve this problem without using any data structure, and then whenever there will be a requirement, we will be using a data structure. Okay, let's try to do that. So let's draw a rooted tree for an example. Let's draw a rooted tree like this. Something like this. Okay. And whenever you have an update at some particular node here, so whenever you have an update that is like not update, let's write this as a walk. Whenever you have a walk of length d from this node, then one obvious way to do this thing is just like do a DFS from here for all the length d, from here and like update their probabilities, right? So for example, when you what is the probability of like visiting this node? Of course, like 1. If let's say like d equal to 2 in this example, okay, so the probability that like you visit this is 2. Probability that you visit this is 1 by 3, because like you have 3 choices here and you can take any of them with equal probability. Then what is the probability that you visit this? So 1 by 3 into 1 by 2 is equal to 1 by 6. And the probability that you visit is 1 by 6, and this is 1 by 3. This is 1 by 3, right? So yeah, that's all that you have. Cool. And then like whenever you have a query, so if you have a query like what is the probability that like this guy was visited, so clearly you can see that the answer is 0 in this particular case. But whenever you have a query like what is the probability that this guy was visited, um, then like you answer 1 by 6. Or if, in other words, if you have a query like what is the expected number of visits for this node, so you say 1 by 6. Let's say like you have another update. So if you have another update from here of length equal to 5, right? Or maybe d equal to 3, or let's take like d equal to 3, d equal to 3. So what is the probability that this guy will be visited? The probability is 1. What is the probability that this guy will be visited? 1 by 3. Now clearly see that I am doing plus because of linearity of expectation that I have already explained. And what is the probability that this guy will be visited because of this random walk? So clearly this is also 1 by 3, right? Because till here you have 1 by 3, and from here you do not have any choice. From here, what is the probability? Plus 1 by 6. And from here, what is the probability? 1 plus 1 by 6, right? So yeah, that's it. And for like, of course, like here also the probability is 1 by 3, here also the probability is 1 by 3, and here the probability is 1 by 6, and here the probability is 1 by 6. So now if you have a query like, okay, what is the answer for this? So you will be like 1 by 6 plus 1 by 6 is equal to 1 by 3. So 1 by 3 is the answer. Now if the query is for this node, then like clearly you see there is only one update, the answer is 1 by 6. This is the answer. Now, if the query is for this guy, then the expected number will be how much? 1 plus 1 by 6. So that is like 7 by 6. So answer this. This is the answer for this guy. So this is how you do it. But if you do it in a naive way, then what is the time complexity? Of course, like for each update you have to do a DFS. So that's the order n times. But each query or straight like each update, you can each walk you have to take this, and for each query you do not need to do anything, just like you answer the query. And if there are q queries, so overall time complexity is order q into n, right? So this is time complexity. Clearly like this complexity is not gonna run. You must be like knowing why. So we are going to look for something better, right? Like then what do you do to solve this problem? Another way to solve this problem is, instead of, so we have seen like two ways, right? One way is like whenever you have an update, just like keep that update there, and when you have a query, then like iterate through all the updates and like find out what is the probability and then like sum it up. The second approach is, whenever you have update, like just traverse through whole tree and uh, update the probability at all the nodes, and whenever you have a query, just answer them, right? Something like this. So this is one approach, and the previous approach was this, right? So whenever you have update, just like let the update be there, and you iterate through each of the update, and using this formula, you find out the probability, and basically you take summation of that. So in this case, clearly each update was what? Each update or each walk was nothing. In this case, each walk was basically nothing. You just need to keep track of that. But each query was of the order q, right? Each query was of the order q. So overall time complexity was order q square. This is the least possible complexity, right? Like yeah. So, or if you like write it in a different way, like if you do a DFS from here, then instead of like each query, like you can also like club some of them, and you can like do a DFS from that particular node in order n time. So basically this can also be order q into n, which is again like not desirable, right? If you do a DFS. You do DFS from query node, right? Instead of like going through each of the query. So like बात बराबर है, दोनों ही केस में inefficient solution है, and इस वाले केस में उल्टा कर रहे थे. So we basically need to find some middle ground, right? So the middle ground is, so the observation or the solution is for each walk go on and update some good nodes, okay, and for each query go to those good nodes intelligently and find the answer, right? So what are those good nodes and all? So basically we are taking a middle ground. So this is nothing but taking a middle ground. This is nothing but taking a middle ground of the previous two approach, right? We are taking a middle ground of the previous two approach. Now what are these good nodes and how do you solve this problem? So let's like go into a little more uh, deeper details, and the answer lies in the centroid tree. And basically like you might also know this by centroid decomposition algorithm, centroid decomposition of a tree. Of a tree. So what do you do in a centroid decomposition? Basically you decompose the whole tree into multiple levels, and for each of those each of those subtree you have a representative node, and those are those good nodes. Like I talked about like some good nodes here, right? So whenever you have an update, like you go to some good nodes, so those will be those representative nodes, and whenever you will have a query, like you again like go to those um, representative node to find. So quickly I will take one example to illustrate like what centroid decomposition actually looks like. For example, this. Centroidly decomposed. Yeah. So clearly by the name you know that like how to do centroid decomposition. So you take the whole tree and you find out the centroid of this tree. Centroid is basically a node such that this is your middle weight. So each of these subtrees from arising from here, none of them are like very heavy or very light. So mathematically, a centroid, you choose the centroid such that weight of each of the subtree I is less than equal to s by 2. S is the total size for all I. So basically whenever you are at the centroid, you have like these four subtrees because of like this, right? So none of them are like very heavy, so that is the idea. You take the middle ground. So when you take this, so this is the representative for the whole tree. This is the representative for the whole tree. Okay, and whenever you have, just a second, let me choose one highlighter. Second, why this is not working? Sorry guys. Yeah, cool. So what do? So this is the representative right here. So let's say like there was any update from here, so you kept that update here, and then let's say like you had like some other update from here, and then like you also kept that update in this representative node. You had like some another update here, so instead of like keeping this information everywhere, like you kept the update here. So anything happens in the tree, anywhere anything happens in the tree, you keep the update here, like in some form. So once you keep this here, then like if there is a query, if there is a query from this node that okay guys, like tell me what is the answer, for example tell me like what is the sum of those probability, then again like you go to the representative node here, and here you tell me you tell this representative node, hey like tell me what is the answer. So the naive way would have been that you would go this guy to this guy, you would go to this guy, and you would go to this guy and ask them for the answer. But in this case, like you have already for all these three values, you have already taken some answer here. So using that value, you directly calculate the answer for this guy. You directly calculate the answer for this guy. Okay. So so whatever is what information you are going to store in this centroid, we are going to talk about this, how we can use this information to calculate the answer for this guy. We are going to talk about this. But basically the idea is whenever anything happens in the tree, you go to the centroid and like keep that information in the centroid, and like whenever you have a query, then you again go to the centroid and you ask that, hey like tell me what is the answer. But here one key thing is missing, you must have like noticed here. So this centroid will give you the answer. This centroid will give you the answer for everything, from like all these subtrees, except the subtree where like this node itself is lying, right? So for that, like you again break this into another centroid tree. So for the another centroid, like what will be the centroid? So this will be the centroid for like this tree, right? Like, so it breaks this into a multiple tree. So you get the answer for everything other than like your own subtree, because like if there was some update from here, then the answer may not be like obvious to calculate for in this case. Why? Because like when you had gone there, like you would keep the update here, and then like when you calculate the answer from here, like you will see like some sort of like repetition. Here it is not obvious why this is happening or why this is undesirable, like but when we actually solve the problem, we will realize that okay, like this is a problem. Because imagine like if you like for this random walk, like what kind of information we can store. So from here, like if there was a random walk from here uh, of distance d, then you can store this information by going here, and then like here you will say okay, like there was a random walk of length d minus 2 from here, and the probability for that you can like calculate this prefix probability. Let's say like the probability that you reach from here to here is pi, so then you calculate this pi. So instead of like keeping the update here, the random walk here, you can sorry guys, instead of that, like you can keep the same information, equivalent information, almost equivalent information in this centroid. And how? Not exactly by saying that okay, a random walk has started with probability 1 from here of length d, or instead you would say that okay, like this is of length let's say like 2. So you will say okay, like a random walk has started from for of length d minus 2, and the probability that a random walk has started from here is like whatever is the probability that you reach this guy. Sorry. Right. Similarly, whenever like some update has happened here, then again like you keep another update here. So d minus 2, because like this length is 2, whatever length like you can minus. And let's say like this probability is p2, so like you say that okay, some another random walk has started of length p2, of length d minus 2 of p2. And similarly, like here you can also store this as a probability 3. So clearly you can see that all these updates, these random walks, which actually has started here, but you have like short circuited that, and you have said that okay, no guys, like they have not started in these so many places, but these random walks have started in this particular node, right? and but you have like modified the information a bit, because like whenever a random walk that has started from here, it will like reach here, so there will be like some particular probability. And to answer what is the probability that it you will visit this particular node, so it is obvious that the probability with which you visit here and into probability with which you visit there for this random walk. um, so you already stored these probabilities, right? Already stored these probabilities, so like you basically need to do p1 plus p2 plus p3 into p4, and this is the probability of p4. Sorry guys, sorry guys. So because all these three probabilities are already calculated here, so you just basically take the sum of like the probability and multiply that with the probability that like after you reach here, what is the probability that you reach the next level. So this is the idea, but like clearly you can see that the same idea is not correct if there is update from here, because if there is update from here and then like if you stored this as a d minus 3 length from here and like some probability px, right, then again if you multiply it by p4, that will be wrong, because the right answer is only this part, right? Like what is the probability to be it from here. So if you go from here and here, like this is not allowed, because you cannot take the same path again. So these kind of updates, they are not solvable. But any update which has happened outside this subtree, outside this like dotted subtree, they will be taken care of, right? Like so these guys, any update that has been happening outside this subtree will be taken care of using this shortcut method. But to answer this, you again do a centroid decomposition here. You again do a centroid decomposition, and you keep on doing centroid decomposition like at each layer. So basically, you divide the tree recursively into multiple centroids, and like you create a sort of like centroid tree. And whenever there is an update, so you at each level you go in the centroid tree and like you update these values. And whenever there is a query, then again like at each layer you go to the centroid tree and find out the answer from there. So this is the idea to solve this problem. Now centroid tree, you can read about it on the internet, like it is a very useful tree in competitive programming problems. And I think Tanuj Khattar has written one good article on centroid decomposition, but there are like many other articles that you can read from on the internet. Read about it. There are like many other use cases. So now coming to the exact specification, like how exactly what kind of information you can store and all. So there are like three basic things. I think there are three basic things. One, some pre-processing. Number two is some updates, and number three is query. Okay, so we are going to talk about like these three aspects one by one: pre-processing, updates, and query. Okay. So we have already talked about how do you calculate the probability that v is visited if there was a random walk from u, right? So we have already talked about this. So this was nothing but 1 by degree of u into product of for all the intermediary nodes. So I belong to intermediary nodes, internodes. You basically do 1 by degree of xi minus 1. So this is the probability that this will visit from here to here. Now how do you find this thing efficiently? So in the original tree, you can, in the original tree, what you can do, you can root the original tree like this. Okay, you can root the original tree like this, and like if you have a query that what is the probability, like this probability, right? This probability uh, that if some update has happened in EU, then what is the probability that you will reach V? So the answer will be nothing but like you go through the LCA and you find the answer. So you need to find the LCA here, right? So there are like many ways to find LCA. You can do some analog and pre-processing to find order one LCA. Just like read about this is a very basic stuff, like how you can do. So you find the LCA, and the answer will be, if you have like some other table, let's call that prefix probability. So prefix probability of any node x is what? It is the just a second. It is nothing but 1 by product of degree minus 1 from the root. Right? Let's call this node C. So clearly here the answer is how much? Answer is nothing but 1 by degree of u into 1 by degree of x minus 1, xi is minus 1. So basically all these intermediate nodes, these are xi's. And also like of course 1 by degree of c minus 1, and then like so on. And let's call this parent of v. The answer will be 1 by degree of parent of v minus 1. Right? Degree of parent of v minus 1. So this is the probability. So how do you calculate this from the prefix probability table? So you can do this probability. Let's call this p. So p is equal to how much? So if you do it from the prefix table, so prefix table may you take u. So what is in the prefix table? Prefix table basically contains the probability from like the root node, right? Like from the root node. So you took the prefix from u, and then like you divide this prefix probability till c. So when you divide it, so basically you have the answer for here. And then like you do multiplication of prefix probability of parent of v, then divide by prefix probability of c. So then like you have the answer from here to here. And then you also need the answer for c. So for that the answer is 1 by degree of c minus 1. Right? So and this, but here like there is a catch. If it were the answer were like degree of u minus 1, then this were correct. But because like you cannot have a minus 1, so let's call this like p dash. So p dash is equal to this, but the original probability will be nothing but p dash into degree of v minus 1 by degree of v. Right? So just like there is this small factor, that is difference between the p and p dash. So if we just like keep track of p dash, then like we are fine. Like you can at any point of time, if you need p, then like you can find p, right? But just by like doing this kind of coefficient multiplication. What basically we did, like here, because of this node u, like you had this thing in the denominator, so we multiplied by the numerator, but the original denominator should have been degree of v. Small math, like you can work it out. So clearly we need to do a few things. We need to find the LCA, right? You need to maintain the prefix probability. So all this thing can be done in the rooted tree if you do the DFS once, and you can like maintain the levels of each of the node. You can read about how to find LCA, keep track of the. So if you like look at this DFS, then what I am doing, you are doing a DFS from node number u, and you maintain. So if you read about LCA, you will know like what is why I am maintaining position in the Euler tree. So I am maintaining the in time, the first in time in the of this node in the Euler array, and then I am using the sparse table method to find the RMQ, or equivalently the LCA in order 1. So these are like some of the values that you need to keep track of. And what I actually wanted to show is like this prefix. So prefix probability of c is nothing but the prefix probability till the parent. C is the child and u is the root, right? Like so far the prefix probability of u inverse is like 1 by. So 1 by tree size minus 1. Like this is the degree, right? This guy is nothing but degree. So degree of c minus 1, and like when you do in, so that this is nothing but like 1 by degree of c minus 1. So this is exactly what I have said, right? Like so this is, you need to maintain the prefix probability. And also I have maintained the inverse of the prefix probability, because I showed you, right, like how to calculate that. Like you also need to divide by the prefix probability of the LCA. So basically when you divide it by the something, that means you multiply by the inverse of this thing. So just like for a smaller calculations, I have mentioned this another array. And how do you answer the probability? So you can see that if u is equal to v, then like of course like you can always visit, so the return is equal to 1, right? Like if u is equal to 1, then always return. Otherwise, if you have to find the probability from u to v, you find out the LCA. C is the LCA, and the answer will be prefix probability of u divided by prefix probability of c. So prefix probability inverse of c is basically nothing but divided by c into prefix probability of v divided by prefix probability of LCA. So and then of course like you need to you need to remove the answer for v, as I said, like I said that like it should be parent of v, like here I said it should be parent of v. So instead of like maintaining the parent of v, I am just like removing it here for the value of v. So this is like removing the value for v, remove for v, right? So if you are going from u to v, note that like you have to only take node u and all the intermediary node, but you don't have to take node v. I have explained this, right? Like therefore like I removed the answer for v here. So removed the answer for v, and here I added the answer for, second, add the answer for the LCA, right? Because like LCA was removed twice, so you need to add it once. And if start is equal to true, that means like if you actually start from u to v, that means like if it is actually probability of u to v and not p dash. So without, if start equal to false, that means like it is get p dash. If start is equal to true, that means like get the probability. So here you can like again see that you divide it by tree size and you multiply it by 1 by tree of size, like the same thing that I mentioned earlier, that to fix that, like from p dash to find the p, you just need to multiply by this coefficient. So this is very simple. This is how you can find the probability that if something has started from you, some random walk has started from you, then what is the probability that you reach v, right? So that can be calculated here. Like we need to find the get LCA. So for that, like you need to LCA, and to find the LCA you need to do Euler tour, and all the pre-processing that you need to do I have already shown in the DFS. Where was the DFS? Here, the DFS. I'm not going to explain like why this, what is this sparse table and how exactly these things are getting found. You can read about that, how to find LCA. Now, how do you decompose a tree into centroid tree? Again, I'm not going to go into the details, but here you can clearly see that I'm decomposing the tree into centroid decomposition tree. Okay, so now let me again remove this screen share and share my good note screen. Yeah. Yeah, so my good notes screen is now saved. You can see, so I have so far like we have seen how to calculate this probability of reaching from u to v. Okay, and I have also explained conceptually how you can use the centroid decomposition tree to find the answer, right? So, as this is considered as a harder problem, so I'm not going to go into details of how to exactly do the centroid decomposition and all that, but that is basically the idea. Now the only thing that remains here to explain, I guess, is how do you update and how do you query. So pre-processing is done, and then how do you update? How do you update? To update in the for the centroid tree, as I said, that like you have broken the tree into multiple levels and call that centroid tree. So you to update at node u, so what do? You do some sort of like while parent of, or instead of like just parent, like let's say the centroid parent. So in the centroid tree, the parent, so while the parent of u is greater than 0, you iterate like at each u, and u equal to parent of. So basically nothing but like you are iterating in the centroid tree. Iterate, you move off the centroid tree. So whenever like you move up the centroid tree from node U, what do? You basically need to keep certain values in that particular node, right? So in that node, what do you need to do? Node dot insert corresponding node of U. So node of U dot insert, and let's call that like something called original U, because U is getting changed, or like also call that V is V equal to U. Okay, V equal to U. So V is the original V that you have been given, and U is getting modified here. So node of U dot insert what? So in this centroid tree, like this, if something has happened originally in node number U, okay, but this is the centroid, this is the original U, right? Like this is the original U, or this is the node V equal to original U, and you are at some node U in the centroid tree. Then what kind of information you need to store? So you need to, and if there was an update of length D, then here what you need to do? So you need to do D minus 2 because like of this length. So D minus 2, and corresponding to D minus 2, what should be the probability? The probability that you go from V to U, right? The probability that you go from U to V. So D dot insert, like what is the distance? If the update was given like D is the distance of the walk, then what you need to do? So D minus, you need to find the distance between V to U, right? So D minus, because like this is the distance between V to U, right? So this, you need to subtract that distance. And what is the probability for that? The probability I already told you how to calculate. The probability to calculate from V to U. So you need to insert in node number U this value, right? Now you also need to maintain something that had started from somewhere. Why? So in all these values, what will happen? So let's go to the centroid tree again and like see what are the three kind of paths that are possible in the centroid tree. So there are three kinds of path. Three kinds of path are, or let me draw another centroid tree, or how can I clear this? Let me clear the highlight. So what are the three kinds of paths that I'm trying to find out now? Just give me a second. Yeah. So if you have a centroid tree like this, okay. So there are three kind of path. This is not clear. So let's use another slide here. So in the centroid tree, like you can have like three kind of possible paths. Right? So if there is a update somewhere, if there were like some updates somewhere here, some updates somewhere here, some updates somewhere here, so all these updates, and there is a query here. So here there is a query. So these kind of updates will pass through this centroid. These kind of updates will pass through this centroid, no issue. But there can also be update in this node itself, right? In this node itself. Now why do you need to maintain like this thing separately? Because like in all these things, you need to multiply this probability as p dash, right? P dash is basically probability such that the walk has started somewhere else, and p is the original probability. That is the probability that walk has started at there, right, at that node. And the third kind of update is this update. So if some update has taken place here, So if some update has taken place here, then also you just something like this. Yeah. So three kind of updates. So some these things that are passing through here. So if you have stored the value here and call that P1, and if you call that probability P2 and you call that probability P3, then clearly what you need to multiply is P1 plus P2 plus P3 multiplied by not the original probability but P dash, and let's call this guy C. So this guy is C and this guy is U. So the probability P dash is basically probably that the this random walk is not started here, right? And the difference between P dash and P I have already clarified earlier, right? So you need to do this. Plus, if some update has happened here, some update has happened here itself, then let's call that PC. Then you have to do PC into, like, this is the one update that has happened, right? One, or PC is the number of updates here. So all the updates that has happened here into P of C to U, right? So P means like the walk has already started from here. So therefore, like, you need to maintain another container. Plus, but in this container, like in P1 plus P2, P3, if there were an update like this, then this P5 was also stored, right? Then this P5 will also be stored here, P1 plus P2. So along with this, like, plus P5 will also be calculated, but we need to remove the P5. So what you need to do here, you need to do minus P5 into the same thing, P dash C to U, right? You need to minus this guy because, like, this thing is not valid. You should not have added this thing in the first place. Now, how do you remove this thing? So to remove this thing, when you update, you need to maintain that, like, for this particular edge, what are the updates that has happened to this node through this edge, right? So we also need to maintain to remove this. We need to maintain for each edge, maintain updates to the center through it, right? So similarly, like, you maintain, like, what are the there are, if there are like total 4 updates, then, like, which of the updates has come through this, which of the updates has come through this, which of the updates has come through this, and which of the updates has come through this. So if you know this information, then, like, you can clearly subtract this information. Okay. So whenever that means, like, whenever there is an update like that, so if you have updates like this, and whenever, like, you have updates that is coming from here, so whenever, and this is the centroid, so you maintain that, okay, like, so something has happened because, and with this probability P1, but with along with that, you also maintain another container that, okay, like, that has happened through P1, and if some another update has happened from here, and that, let's call that P2. So in this node, you will of course maintain P1 plus P2, but in for this edge, like, you separately maintain this P2, right? And similarly, this P1 should be separately maintained. And if, like, some update has happened because of here, and the probability is P3, then of course, like, here you will maintain P1 plus P2 plus P3, but for this guy, you also need to separately maintain P3, because then only, like, you can subtract this kind of unwanted information, right? Like, you can subtract this kind of unwanted information. So that is the idea. So therefore, whenever you have this, so node of u dot insert d minus dist of v minus u, because of, like, you subtract this distance, so the remaining distance is from here, like, what is the distance, so d minus dist of v minus u, and probability of v to u. Now you also need to maintain for that particular edge, right? Let's call this particular edge E. So let's call this particular edge E. So the edge through which this update is happening. So for that particular edge, you also need to maintain the same thing, that, okay, like, this value has been updated through this edge, right? So this update had happened through this edge. Now if this thing is true, if now also you need to maintain if u is equal to v, that means this is the first thing that is updating, like this guy itself, right? In this case, like distance of v to u will be 0, but then also like you need to maintain these things separately, right? So for that particular case, you can do node of u dot insert d, and the probability is of course 1. So you need to maintain like these three things. So in each of the nodes, like you need to maintain three things. One thing is all the updates that are coming from somewhere to this particular node. Then you also need to maintain what are the updates that has been passing through a particular edge, and then also you need to maintain what are the updates that are getting initiated from here. So once you have all this information, you can answer the queries efficiently. To answer the queries, if you are at particular node E and the original query has happened with V, this is the original query, then the answer is, and if this distance is D, then to answer this query, this will be how much? So the probability that into moving from U to V multiplied by sum of probabilities Pi such that their corresponding distance is greater than equal to dist of u to v, right? So that means like if there were like some updates that has been coming to here, and then like you have stored all this information, along with all these updates, like you have maintained two values, right? Like d and p. So d is the remaining distance and p is the probability. So of course the remaining distance d has to be greater than the distance of u to v. So that, and then like you take all of these pi and sum that up, and of course like that was the probability that you reach till here, and to reach till v you also need to multiply that by probability from u to v, right? Then also you need to do probability of u to v into sum of all pi such that the walk has started from here. The walk started, sorry, like this should be p dash and this will be p, because yeah, p dash, because like from here till here, like you have already know that like the walk has started, but for this remaining part you know that like the walk has not started here, so therefore like this should be p dash, and p means if some walk has already started here, so it should be p, so such that the walk has started from here. You need to do, and also you need to subtract some value. So if you know that this is the edge E, right, if you know that this is the edge E, then you also need to subtract the probability again, like this p dash u to v into summation of all pi's such that the walk has passed through E, right? So here you have added everything, here you have removed, so you need to do this like minus, right? So and here like you remove everything that has already passed through this. So any update that has happened from any of the child in this subtree, and like you have stored this information, so you need to remove this information, and to remove this information you need to remove everything that has passed through. So like you remove this information, and this guy is what? This guy is about like all the updates that has started from there, from you. Okay, so that's all guys, like how do you solve this problem. And to answer like all these small sub part of the problem, like how to find the LCA, how do you maintain like if something is greater than distance d or not, these things are very like standard.